Now the point is, right, this particular thing, okay, that you have, right, this expression which is V is equal to AU A transpose, right. I want you to write. So we'd like to show that there is an alternative way of writing this. Okay, there is an alternative way of writing this kind of a matrix product in terms of using a Kronecker product. Okay, and that it's a kind of a standard result. Okay, that is actually well known. But since you people may not have been introduced to a Kronecker product or matrices, I thought we'll actually derive it. Okay, so in general, okay, we would like to look at if I had something like A U B transpose, okay, wherein I don't care what A U and all mean. For example, we don't even have to assume that A is unitary and all of that. Some arbitrary matrix A is given, some arbitrary matrix U is given. Of course, you should be able to multiply them. Okay, that compatibility should be there. But otherwise, right, we don't care what they are. So B could be something else. Okay, suppose we just come out of this image transforms completely and simply look at a situation where I have a product like this. Right, somewhere in some application when you encounter some AU B transpose, then there is a way to actually write this using a Kronecker product, and that is valid for any AU B. Okay, it doesn't have anything to do with image transforms, by the way. And then if you have that result, right, then you can invoke it for your problem. Okay, so for example, I mean in your case also, right, you can write this as B transpose if your image is not square. Correct. If it is not square, then of course you'll have to write it as AU B transpose, which will be the same, which will be of this kind, right? So we want to know what is this form, right, that we can utilize, okay, which is a standard result that we would like to utilize it. In fact, I mean, the way these people go to higher dimension is actually using this result only. Okay, since you may not have seen it earlier, I thought we will show it here. Okay. So prior to that, let's just talk about what really is this guy, the Kronecker product. Actually, this is an interesting product. I kind of leave it to you to find out more about it, because all that we will need are some elementary things. But it's actually a very, very interesting sort of a product. Okay, Kronecker product of two matrices. Some of you, right, who are more interested, in this kind of matrix operations and all, it can go and sort of investigate it more. But it works like this. Suppose I had A is equal to, let's say, some A. Okay, now we are walking away from image transforms. Okay, now whatever I write is some arbitrary matrix. None of this unitary and all is there. Okay, so this is out of image transforms. Okay, we are out of it, and we are just looking at just matrices. Okay, so let's say A is equal to A00, A01, A10, A11. Right. Suppose I have this, and suppose I have another matrix, right, B, which is, let's say, B00, B01, B02, something like a 3 cross 3. Okay, B10, B11, B12, and then B20, B21, B22. Okay, so if I have something like this, then when you kind of talk about a Kronecker product, the symbol is a cross, inscribed in a circle, and when you say A cross A, this one. Okay, so this is a Kronecker symbol. Okay, this is a standard symbol. Okay, A Kronecker B is now this new matrix, that is A00B, A01B, A10B, and A11B. Okay, so it simply means take the first entry of A, multiply it with all of B, and then take the second entry, multiply it with all of B, third entry, whatever, right? So an operation like this, right, you might actually wonder, so what, right? I mean, if one can do this, then how does it impact us? It does impact us in a big way. Okay, we'll see that, okay, in a minute. But then prior to that, let me also list out a few things about a Kronecker product. Oops, kind of, I don't know what happens, huh? Okay, so it actually means that, so for example, right, in general, right, do you think A Kronecker B, can it be equal to B Kronecker A? Right, in general, okay, right, it's not true, but you can actually think of some kind of trivial cases where you can show that this will happen, but in general, okay, it won't happen. Okay, A Kronecker B is typically, what about the size? I mean, can we say that both will have the same size? A Kronecker B and B, right? True, because if A is, let's say, M cross N, and then if you're taking its Kronecker product with B, let's say if it's P cross Q, right? It doesn't have, they can be whatever size they are. So then if you take this Kronecker product and suppose you call that C, then C will have MP cross NQ, right? Because it's like saying that So it's like saying the rate. I mean, every time you multiply A00, okay, with this B matrix, right? Then you already have if B has P rows, then for every element you have P rows, and you've got like m number of rows in A, right? So it'll be like P times M. That'll be the number of rows. And similarly, in terms of the columns, once you multiply, you'll get like as many columns that B has, and then multiply it by the number of columns that A has, right? So you'll have MP cross NQ, and if you do B Kronecker A, right, that will also be the same, right? If you do this will also give you some other matrix, probably D, and then we see that is PM cross QN, right? Size will remain the same, but these two matrices, right, will typically not be the same. What if right, what if, let's say, AB is equal to BA? Can you, right, I kind of leave it to you to check what your first impression is. Like what? A gut feeling. What if AB is equal to BA? What if, let's say, A and B are such that, right, A into B is equal to B into A? A gut feeling would be what? Yes, Vignesh? Both are? So fine. No? So what? I mean, but I'm asking, no, if this is true, then do you expect that A Kronecker B might turn out to be equal to B Kronecker A, or you seem to feel that, okay, that may not impact it? Yeah. Anyone else? Shankara, what is your name? Shrikant. Shrikant. What do you think? Anyway, right, I kind of leave it to you. Okay, you can kind of think about it. Let me list down a few more properties, okay, of this product. Not all are going to say relevant to us, but I think just it's good to know. Okay, we won't use all of this. Okay, some additional properties. I thought since we are on it, right, I just thought I'll kind of list them. One is A plus B Kronecker C is A Kronecker C plus B Kronecker C. Okay, this is one property. Then A Kronecker B into C Kronecker D is equal to AC Kronecker BD. Yeah, of course, in this case, you have to make sure that A and C you can actually multiply, right? They have to be compatible. So the second property requires compatibility. It's not automatic, no? Right? So provided A and C are compatible, B and D are compatible, right? Then A Kronecker B Kronecker C is equal to, you would kind of guess that should be A Kronecker B Kronecker C. Then what do you think about this alpha A Kronecker B, where let's say alpha is some is a constant? What do you think this might be equal to? Yeah, you. Correct. So what do you think it might be like? Alpha A, I can do Kronecker B, or I can also do A Kronecker alpha B, right? That should also be fine. A Kronecker alpha B. Then A Kronecker B transpose. What do you think it might be like? A transpose Kronecker B transpose, right? This is unlike the AB transpose, where it is B transpose A transpose, right? A transpose Kronecker B transpose. Then what about A Kronecker B inverse? A inverse Kronecker B inverse. A inverse Kronecker B inverse. But this last one, right? Anyway, simply out of interest, not that we are here to do a lot of matrix theory, but I'm just can let's say, can one of you tell me what will be the rank of A Kronecker B in terms of rank of A and B? Can anybody make an educated guess of that? You can see the way this operation is, right? A Kronecker B, the way it multiplies and goes on. What do you suspect must be the rank of A Kronecker B? Minimum? Sorry? No, in terms of rank of A and B. In terms of minimum of both. Multiplication of both, exactly. It's rank of A into rank of B. Rank of A into rank of B, okay. Which will also mean that, right? I mean, if you had to write this, right? I mean, so what do you think that if A is not invertible or let's say B is not invertible, would you be able to write this? You can't, right? This itself holds only if both right A and B are invertible. Otherwise this inverse itself you can't right individually do at all, because I mean, right, you can see the rank, no, right? I mean, if you kind of write, I mean, if you use this rank result, you should be able to show. But again, right, we are not showing why the rank is so and so on. Anyway, right, that's simply out of interest. Okay. So the point is this, right? If you have a Kronecker product like this, okay, which is what it is. Now what we would like, some of these we will use, but not all of these properties. Now, if you go back to that expression, right, that I said that we wanted to, I'm struggling. This is 2, 3. Okay, now if you kind of if you simply examine, okay, if you examine V is equal to A U B transpose, okay, where A U and B are all right arbitrary matrices. By arbitrary I mean they don't need to be unitary and all, are some arbitrary matrices. Okay, we want to be able to invoke this. There is an excellent article just on this. There is a Kronecker product article on that. I mean, he says on the ubiquity of KP. Okay, read that article. It's a fantastic article for those of you who want to know more about this Kronecker product. What kind of decompositions has it been used for? In fact, right, there is a whole lot of theory that builds upon all this multidimensional signal processing on this Kronecker product. Okay, so for those of you who are interested, at least read that article. Very old article, but that's one of the excellent articles on this. I mean, he starts right from the basics and goes all the way up, right? How you can exploit it for signal processing applications and so on. Golub and Van Loon. Okay, so V is equal to AU B transpose, right? So the point is, okay, now let us say, okay, so I'll show it for a small example, right? A 2 cross 2. I'm going to show it and then I leave it to you. Write a MATLAB code and then show it for any case. Okay. Now let V have entries V00, V01, V10, V11, A. Okay, this we would like to finish today. Okay, at all costs. A00, A01, A10, A11, U. U00, U01, U10, U11, then B. Okay, B00, B01, B10, B11. This is what it is. Okay. Now let VK and what is this UM denote the kth and mth rows of mth rows of V and M, V and U respectively. Okay. Now if you take V transpose, so V transpose is what? B U transpose A transpose, right? Now let's just write down V transpose. Okay, V transpose from the above is V00, V01, V10, V11. Okay, this is equal to, okay, so suppose we call this V0 transpose, we call this V1 transpose. Okay, this column is this. Okay, then B, now U transpose, U transposes U00, U01, U10, U11, and then A transpose, which is A00, A01, A10, A11. This is what it looks like. So if you multiply this, right, what do you get? You get B U00, A00 plus U10, A01. U00 A10 plus U10 A11 U01 A00 plus, oh, probably you guys read Strang maybe, right? That is your U1 U01. Okay, so this is what you have, right? Now, if you sort of examine the first column, okay, of V, okay, which is this V0 transpose. Okay, now if you examine the first column of V, right, that I can write as B summation. In this case, I'll write it as M equals 0 to 1. See here, right? I mean, it's like, you see, A00, okay, which is actually multiplying the first column. Okay, so let's call this as U0 transpose. Let's call this as U1 transpose, right? So if you see, okay, A00 multiplies U0 transpose, which is the first column of U, and then A01 multiplies the second column of U, right? So this you can write as A0M. After all, A0, right? A00, these are all scalars, right? So A0M. And then UM transpose, because it is, right, because it is of this form, no? Okay, which also means that because A0, because, right, this guy is after all a scalar, so we can actually send it inside as M equal to 0 to 1 A0 M B UM transpose, right? After all, A0 is a scalar, so we can push B further in, right? So one thing you have is this, right? So I'm sure, right, you all agree. Now V1 transpose will then be what? So V1 transpose, if you see, right, that is the second column, that is coming as A10, okay, that is coming as the second column of right, this guy, okay, A10, which is sitting here, and then A11, right, which is sitting here. And then it is again multiplying the first column of U and then multiplying the second column of U. So following the same thing, the summation M equals 0 to 1. Now it will be A1M, right, because it is A10, A11, no? So A1M, and then again it is UM transpose. Or this can be pushed in, and then you get M equals 0 to 1, then you will get A1M B UM transpose. Agreed? Right. Okay, now suppose I can say stack these two up. Suppose I stack V0 transpose, I stack V1 transpose like that. Then can I kind of write this as, I will stack here U0 transpose, I will stack U1 transpose. By stack, right, I mean that, see, V0 transpose is simply, right, you take the first row of V, and then if you were to make it into a column, then V1 transpose like the second column, second row of V, right, put as a column, correct? So you're like stacking one column below the other. Then V0 transpose we know is what? A00 B U0 transpose plus A01 B U1 transpose. Then V1 transpose is A10 B U0 transpose, A11 B U1 transpose. Okay, now if you see this result, right, this is not something that you have seen before, right? This is simply a Kronecker product of A with B. Okay, and I just took a 2 cross 2 for simplicity, just to show here, right, on the board, but this holds for any size. Okay, so what this means is that then this boils down to V0 transpose V1 transpose is equal to A Kronecker B. Okay, and it is A Kronecker B and then multiplying U transpose. Okay, this is whatever, right, U0 transpose U1 transpose. I mean, it's not like I mean, no, you can't separate it out. You can't do first A Kronecker, I mean, you can't do B times U transpose and then do this an A Kronecker. Okay. So U0 what is this? U0 transpose U. Okay, so which is the reason why I have enclosed this in bracket. Okay, so you have to first compute A Kronecker B, and that should multiply U transpose U0 transpose U1 transpose. Now if we further write, okay, if let, right, this vector V represent V0 transpose V1 transpose, and let this vector U represent U0 transpose U1 transpose, then it's clear that I can write V as A Kronecker B times U. Now if you see, right, this expression is exactly equivalent to V is equal to A U B transpose, okay, and as I said, I am not assuming anything about unitariness or anything, right. This is in general true. So for example, if let's say, okay, if V is if let's say U is M cross N, okay, then B will be M cross N cross N, A will be M cross M, and V will be M cross N, okay, in general. Which then means that you know, if you stack this matrix up, right, in terms of a column, so this guy's dimension V will be Mn cross 1, correct? You will stack it up as a vector, no? Mn cross 1, and then when you do A Kronecker B, right, that will have a size which is M. Hey, what happened? Did I? Which is? No, wait a minute. A Kronecker B is Mn cross Mn, right? Mn cross Mn, and then you multiply it with U, which is Mn cross 1, right? So I took 2 cross 2, but it doesn't matter, right? You can have right, something like this. Now, what exactly are the implications for us, right? This is a standard result, okay, and you know, you may underestimate it, but this is a very, very key result, okay, which has been, you know, used in several places. But now if you come back, right,